Hey everyone! I am Miss Hu, your physics teacher. In this video, we will be going through the concept of motion graphs. What we will be covering in this lesson are distance time graphs, displacement time graphs, speed time graphs, velocity time graphs, as well as acceleration time graphs. So in this video, we will be going through an overview of these graphs. If you'd like to find out how to solve questions involving these graphs, that will be covered in separate videos. If you have any requests, feel free to put them down in the comments below, and I'll do my best to get those videos up as soon as possible. For now, let's move on to understanding more about these particular motion graphs. Here's a little meme for you. So if, let's say, your partner wants some time and distance, is she calculating speed? Alright, so in case you didn't know, I like memes and lame jokes. I just found this funny. But anyway, let's move on. So first things first, let's go through the concept of gradient and area under graph in general. Because if we want to analyze motion graphs, we may need to use the gradient and area under graphs to get further information. So before we go into that, let's have an understanding about these concepts first. So let's talk first about gradient. Now, depending on how your math teacher teaches it, you might use any one of these following formula. So if this is the y-axis and this is the x-axis, you might use a formula of y2 minus y1 over x2 minus x1, or you might learn it as change in y over change in x, or you might learn it as rise over run. Whichever formula you use, they're actually the same thing, because when you look at whatever's on the top of the fraction, they're all the change in y. So the rise is the change in y. Whereas if you look at the bottom, it's the change in x. Run is a horizontal calculation, so it's the change in x. So what we're going to look at in the following motion graphs is what the value of the gradient represents in each of those motion graphs. So as a summary, I'm going to write here that the value of the gradient is equivalent to the variable on the y-axis divided by the variable on the x-axis. So bear in mind that the equation I've written here is not the formula for the calculation of gradient, but rather this would just be a simple note to find out what the gradient of that graph is equivalent to. And now, let's take a look at the area under the graph. So for the area under the graph, you would look for the section that is under the line of the graph. So let's recall, when you want to calculate the area under the graph, it has to be within two coordinates. Let's say we're taking the entire graph. For the first graph, it's from beginning to end. We drop vertical lines from both points down to the x-axis. Area under the graph is encompassed by these two vertical lines, the line of the graph, and up to the x-axis. So as you can see in the first graph, the area is a rectangle. For the second graph, if we were to take again from the start to end, we drop vertical lines to the x-axis, and again the area is encompassed by the vertical lines, the line of the graph, and the x-axis. And as you can see, this time this is a triangle. I'm just going to make this a little bit straighter. And for the third graph, again, let's look at the start and end. And you can see from this graph, this forms a trapezium. So when you calculate the area under the graph, you would use the same methods you have learned in mathematics, which means that for the rectangle, you would take the width times the length. For the triangle, it's half base height. And for the trapezium, you can calculate it either by using the formula of the trapezium, which is half bracket a plus b times the height, or you can divide this into three sections: triangle, rectangle, triangle, and you get the sum of those areas. Whichever method you use, as long as you're calculating the area for that particular shape, it applies. But what we're here to talk about is not how you calculate the area, but what the area would represent. So let's look in general, whichever the case. So for the rectangle, you would calculate length times width, which means that the area is essentially x times y. So I'm going to put xy. For the triangle, it's half base height. The base is x, the height is y. So I'm going to write here half xy. Whereas for the trapezium, you can use the area for the trapezium, which is half, let's say, x1 plus x2, if say this was the length of x1 and say this is x2, and then multiply it with the height, let's say this is y. Now, whichever the formula you use, you can see there's a product of x and y involved. Even though there may be coefficients such as half and there's an addition here, but when you really get down to it, it's quite simply x times y. Whatever factors you have here is just modifying the value that we take. So instead of taking an entire rectangle, we take half of it. Instead of taking the entire rectangle, we would remove some parts of it. It's still x times y. So later, we're going to take a look what the value of the area under each of those respective motion graphs represent. So for now, I'm just going to write in general that the value of the area under the graph is equivalent to the variable on x multiplied by the variable on the y-axis. Alright, so now that we know about gradients and area under the graph, let's look at those individual motion graphs. So now let's take a look first at distance-time graphs. So students, remember that every time you are presented with a graph, the first thing you need to do is look at what's on the x and y axes. This is so that you know what kind of graph you're looking at, and from there, you will be able to analyze them correctly. Now, let's look in general first. So a distance-time graph basically shows the distance covered by a moving object. All you need to do is just use your logic to understand the graph first. So, for example, if you have a part of the graph where you find that it's 0 for a certain amount of time, think about it logically. 0 means that 0 distance is covered. That means during this time, the object is stationary or at rest. If you get the part of the graph where the distance is increasing, obviously that tells you that the object is moving. If there is an increase or decrease, so whether it's a curve up or curve down, whichever the case, it's still moving. The difference between all these three sections is at what speed are they moving at. And that's what we're going to be learning on the next slide. For now, let's just finish up. If we have another part of the graph which is parallel to the x-axis like this, although there is some distance, so to speak, but you can see that from beginning to end, the distance hadn't changed. That tells you that for this section of the graph, it is actually stationary. So what this distance-time graph is showing us is where the object is relative to its starting position. So here is 0, which means this is the starting point. It was stationary for a while, then it moves. In this case, it's a linear graph. It moves, but this time there's some changes in its way it's moving, giving us some curves, and in the last part is stationary. Now, students, just a reminder that distance is actually a scalar quantity. It's not a vector quantity, so that means there's no direction. There are two possible kinds of distance-time graphs you might get. One is a distance-time graph that shows the distance the object is from its starting position. So, for example, if this is the ground and this is the object, and this is the starting point where it began from, it is possible that the object might move and turn back. So if the distance-time graph is showing us the distance from the starting position, it might be possible for the graph to show a backward movement. So this depends on the kind of graph that is being depicted. However, if it's a total distance traveled kind of graph, the graph would never go backwards, because if you recall, for distance, regardless of whether it's moving forward or backward and going in the opposite direction, the directions don't matter, which means that the distance covered is the total distance, which means that even if it's going backwards, the distance covered is still increasing. So you should never see the graph dropping down towards 0. It'll always be a continuous increase. Sometimes in the questions they don't tell you this clearly, but I just want to point this out because there are two trains of thought on this. So there are some who say distance is scalar, there's no vector, it should never go backwards. Yet oddly, you might come across questions in the exams where the graph goes backwards. So if you see the graph dropping towards the x-axis, that means this graph is showing you the distance of the object from its original position. So the distance is referring to the distance at where it is throughout the entire point and not the total distance covered. So anyway, let's move on to the next part. So when we want to analyze a graph, it's not just about saying, oh, it's moving, oh, it's stationary. You got to remember that in physics, we're always trying to find a way to measure the values. And if we could find a way to numerically represent the values accurately, that's the method that we would use. So remember that earlier we just talked about gradient and area under the graph. Now let's take a closer look at those two concepts. So calculating the gradient and area under the graph would give us additional values that we can get to analyze the distance time graph. So if you recall what we had written earlier, the gradient is equivalent to whatever is on the y-axis over whatever is on the x-axis. So if we look at this graph, you'll find that distance is on the y-axis. So I'm going to replace y with distance. Time is on the x-axis, so that's going to replace x in this formula. Now you can see that if you were to calculate the gradient of a distance time graph, you would be getting the value of the distance divided by time. Look at this closely. Does this look familiar? Is there any variable you know of which is equal to distance over time? That's right. Speed is equal to distance over time. So I'm going to write that out. So speed is distance over time. So you can see that in these two equations, they're equal to the same thing. So what this tells us is that if we were to calculate gradient, the value of the gradient would be equal to the speed of the object. So what does this mean? This means that if you calculated the value of the gradient, that number is equal to the speed of the object at that time. And whatever the gradient represents, it represents the speed. So to further prove this, you can also check the units. So let's use the SI units to understand this. The SI unit for distance is meters, while the unit for time is seconds. And this gives us meters per second. Meters per second is the unit for speed, and this further proves that gradient is equal to speed. So what did I mean when I mentioned earlier that whatever the gradient represents, that's the speed? If we look back at the graph, say for example, we have a graph that is horizontal like this. I'm just going to draw it above the x-axis. If you have the section of the graph that is parallel to the x-axis, the gradient value is how much? Let's try to recall our math. That's right, the gradient is 0. Because the gradient is 0, this tells us that the speed is 0. And if you recall what we've just covered in the previous slide, a horizontal line means the distance hasn't changed throughout this entire time, which means it's not moving. Not moving means 0 speed. So can you see how the gradient accurately proves this? In this section, the graph is linear. That means the gradient for this section is constant. Whatever the value is, the gradient throughout this entire section is constant. So I'm going to write here, constant gradient. Constant gradient means constant speed. And if you try to analyze this, this should make sense because you can see that the distance is changing at an equal ratio throughout the time. So that means the speed is constant. Constant gradient, therefore constant speed. Now, if you get a graph where the section has a changing gradient means changing speed. So if you look, it should make sense, right? Because initially the distance doesn't change very much, but then the distance starts changing at an exponential rate. This section shows us an increasing gradient value. So that means the speed is increasing. Is this starting to make sense? So anything that you get from the gradient, that's what the speed is. So if you have the section of the graph with a higher gradient, that means higher speed. Lower gradient, lower speed. So whatever we get from the gradient, that's the speed of the object at that section or that point in time. Now, for those of you who are wondering, what about the area under the graph? Let's take a look. So in the earlier slide, I wrote area under the graph is x times y. In this case, x is time and y is distance. So going to replace that with time multiplied with distance. Is there any variable you know which is equivalent to time times distance? None that comes to mind, right? So this means that the area under the graph, in this case, does not represent anything. So remember that just because we can calculate it, and you can count, oh, here's a rectangle, here's a trapezium, and so on and so forth. You can calculate the area, but that doesn't mean it necessarily represents anything. So in physics, we look at the practical meaning of what we're calculating. Just because you can calculate it doesn't mean we need to use the value. So if there's no meaning ascribed to that particular calculation, we can ignore it. So for distance time graphs, area under the graph is not used as part of the analysis. Gradient, yes, because the gradient is equal to the speed. So to take a quick overview again of distance time graph, here I've got 4 general graph shapes. So in the first graph, you can see that the distance does not change, or in other words, the gradient is 0. So because the gradient is 0, that means the speed is 0. For the second graph, the gradient is constant. That means the speed is constant. For this graph, it's an exponential graph and the gradient is increasing. So an increasing gradient means the speed is increasing. And for this graph, the object is still moving, but the gradient is decreasing. A decreasing gradient means that the speed is decreasing. So to understand these two graphs, for this graph, as you can see, it starts off with a speed that is 0 because it starts off with a 0 gradient. And as time passes, you can see that the distance is increasing exponentially. So it makes sense, the speed is increasing. Whereas in this graph, you find that it starts off with a very high change in distance, but it levels out to eventually become 0 gradient. So therefore, we find there's a decreasing speed. So that's for distance time graphs. Now let's look at speed time graphs. So again, just a quick understanding of speed time graphs. This time for speed time graphs, they're showing us what the speed is for the object at that point in time. So it's showing us the instantaneous speed. So instantaneous speed concept is something like if let's say you're driving and there's a speed trap police is pointing this device to you and it captures, that's the speed of the car that's moving at that point in time. So if it's a high speed, that's what it'll show up. So instantaneous speed is the speed of the object at that point in time. And a speed time graph shows us that. So if you have a graph like this is 0 speed. So that means that the object is not moving. Now, if you have a graph like this, you can see that the speed is increasing from 0 to a particular value. So here, you'll find that the object is moving. And the speed is increasing. So I'm going to write here, moving with increasing speed. So regardless of the shape, as long as the line is moving up, whether it's a curve this way or curve that way, the speed is still increasing. It's just that the speeds are increasing at different rates for these three sections of the graph. Now, if you get a graph which levels out like this straight line does not mean it's not moving. It's moving. There's a particular speed value, right? Here, the graph is moving with constant speed because the speed is the same from beginning to end of this section of the graph. So now, let's analyze this further by looking at the gradient and area under the graph. Let's get straight to it. So we know that gradient is y over x. So we're just going to take what's on the y straight away and put it on top of the fraction. So that's speed, and the x-axis has time. So it becomes speed over time. Now, are there any variables you know of that are equivalent to speed over time? So here's the thing. For many of you, you've learned about scalars and vectors. So some of you are going to find this next part a little bit confusing. Just to let you know, there are some curricula which do not cover velocities until at a much higher level. So you'll find that, to your surprise, there may be some students who learn speed as something similar to velocity. They're not the same, but I'm going to cover this anyway because this comes out in some of the exam questions that you have to answer. Some of you learned that acceleration equals to the change in speed over time. Yes, I know. Some of you will be like, hey, no, it's not. Acceleration is change of velocity over time. And you are right. I'm going to be covering velocity time in the later part of this video, so you can stick around or skip to that part. What I'm covering now is for those students who did not learn about displacement and velocity. They've only learned about distance, speed, and acceleration. So if you are one of those students learning this, then this is what you would have learned. Acceleration is a change in speed over time. So for now, like I said, I'm just going to cover this for the benefit of the students who learned this formula that acceleration is speed over time. Let's move on so that we know how to solve this. So from here, you'll find that gradient of a speed time graph is equivalent to acceleration. And just like earlier, if you want to prove this by means of the units, we can. Look at the gradient equation. We know that speed is meters per second and time is second. Meters per second divided by second gives us meters per second squared. Meters per second squared is the unit for acceleration. So this proves that, yeah, gradient is, in this case, equivalent to the acceleration. So if we were to relate this to the graph, here, this kind of graph gives us zero gradient. Therefore, the acceleration is zero. If we have a graph with constant gradient, this means that the acceleration is constant. As you can see, the speed is changing at a constant rate. That means the acceleration is constant because acceleration is, in this case, the change in speed with regards to time. So I hope you're getting the hang of this, where whatever the gradient is representing, that's the value, which in this case for a speed time graph is acceleration. So even if it's a curve graph, changing gradients, changing accelerations, and if you get a straight line graph like this, this means constant speed. Constant speed, zero gradient, zero gradient, zero acceleration. So if you can recall what you have learned about acceleration, zero acceleration could either mean the object is not moving or it's moving with constant speed. And from this graph, you can see that this proves both. Zero gradients could either mean zero speed or zero acceleration. I know my writing is terrible. Please write better in your exams. I'm just trying to move this on a little bit more quickly. Now, in addition to gradient, we've also learned about area under the graph. So let's look at how the area under the graph could be used in this speed time graph. So earlier, we had summarized that the area under the graph is what's on the x-axis multiplied with whatever's on the y-axis. So we can write this as time times speed. So can you think of any variable which is equivalent to time times speed? Yes, it is distance. So in case you could not get that, let's recall what the formula for speed is. So we know that speed is distance over time. So if you rewrote this formula by bringing time up, you would get distance as time times speed. From here, we can conclude that the area under the graph is equal to distance. And this can be proven with the unit. Let's look at the formula for area under the graph. So we know that time is in seconds and speed is meters per second. Seconds times meters per second, you'd cut the seconds, you're left with meters. And meters is the unit for distance. So this further proves that area under the graph is equivalent to distance. So in this case, similar to gradient, whatever the area under the graph represents, that's what the distance is equivalent to. So for example, in this section of the graph, you can see that there's no area is 0, so the distance covered is 0. Here, you'll find that you have a linear graph and the shape is a triangle. So if you were to calculate the area under this graph using the triangle formula, that would be the distance covered during this section. Likewise for all the others. So if we do a quick comparison between these 4 different shapes, let's start off with gradient first. From the first graph, we have 0 gradient. This means that the acceleration is 0. And if you recall, 0 acceleration, let's look, is this true? Yes, in this case, the speed is constant. So I'm going to add that note here. For this graph, we have increasing speed at a linear rate. It's a linear graph, so the gradient is constant. A constant gradient here means constant acceleration. Constant acceleration means speed is increasing at a constant rate. So that's true. For this graph, we have a graph where the gradient is increasing from a 0 gradient to a high gradient. So an increasing gradient here means increasing acceleration. And for the fourth graph, we have a graph which starts from a high gradient dropping to 0 gradient. So that's decreasing gradient. A decreasing gradient graph for a speed time graph means that it has decreasing acceleration. And for all of these cases, remember that the area under the graph represents the distance. So for a quick comparison, let's look at the first 2 graphs because they're the easiest to compare side by side. If you have a situation where the speed is constant, you find that you'll get a rectangle, so that would be the distance covered. Whereas for a linear graph like this, you get a triangle. So think about it. The area of a triangle is only half of the rectangle, definitely less than. And think about it in real life. If an object is moving with a constant speed, how much distance would be covered compared to if the object starts from 0 and increases its speed with time? Obviously, the distance covered will be less than if it were moving at a constant speed. So if you look at it numerically, makes sense. A triangle has a smaller area than a rectangle if the final speeds were the same. So this numerically also shows us the relationship between the area under the graph and distance. So that's for distance time and speed time graph. Remember that these 2 types of graphs are not the same. So the same shape does not mean they have the same motion. If we do a quick comparison, just to show you, Some students get confused because when they see a flat shape, oh, object is not moving. That's not necessarily true. For a distance time graph, a horizontal graph like this, because the distance is not moving, then yes, in this case, the object is not moving. It's stationary, it's at rest. But if you look at a speed time graph, this tells us it's moving with constant speed. It does not mean that it's stationary. Likewise, for a linear graph, for a distance time graph, if you get a linear graph like this, this tells us the distance is increasing at a constant rate. This is constant speed. But for a speed time graph, the speed is increasing. So it's an increasing speed at constant acceleration. So same shape does not mean same motion. So like for the last two graphs, this is increasing speed, while this is increasing acceleration. And for the fourth graph, for distance time graph, this is decreasing speed. And for the speed time graph, this is decreasing acceleration. So the same shape does not necessarily mean the same motion, but sometimes you might get two different graphs which represent the same motion. So for example, this graph shows us constant speed, and so does this graph. So for a speed time graph, a constant speed with a zero gradient shows the same motion as a distance time graph with a linear line. So these two are actually showing the same motion. Similarly, for the speed time graph, which has an increasing speed at constant acceleration, this might be the same as a curved graph for a distance time. So same shape is not the same motion, but you can still get two different graphs showing the same motion, but of course with different shapes. As long as you can understand how the gradient relates to the different quantity, you should be able to work it out. So now let's move on to the next part of this lesson, where we'll be focusing on the vector quantities of displacement, velocity, and acceleration. Now that we know that gradient and area under the graph can represent additional values, and we know same shape does not necessarily mean the same motion, we can move this section a little bit faster. So just a quick introduction to displacement time graphs. A displacement time graph shows us the displacement of the object related to the starting point. So for example, if this is the ground, this is the object, that's the starting point. Remember how you calculated displacement. Displacement is the direct distance from the start to end with direction. So displacement time graph shows us the position of that object. That means the displacement of that object at that point in time relative to the starting point. And because displacement is a vector, it is possible for displacement time graphs to show us zeros, positives, as well as a decrease. Can the graph dip below the x-axis? Yes, because if you recall, displacement can also be negative. So a negative section of the graph means that the object has moved backwards. So just a quick comparison against distance time graphs. Distance cannot have negative because there's no direction. Negatives only apply in vectors in this case because negative shows opposite direction. Let's go straight to the gradient and area analysis. We know that gradient is y over x. So what's on the y-axis? Displacement. What's on the x-axis? Time. So if gradient is y over x, that means for a displacement time graph, gradient is equal to displacement over time. Now, try to recall which quantity is equivalent to displacement over time. That's right, velocity is equal to the change in displacement over time. So what this tells us is that the gradient of a displacement time graph is equivalent to its velocity. Again, to prove this, with units, displacement is meters, time is seconds. Meters divided by seconds gives us meters per second for the gradient, which is the same unit as velocity. Hence, gradient is equal to velocity. So similar to the earlier graphs that we learned, in this case, whatever the gradient represents, that's what the velocity represents. So if you have a situation where you have zero gradient, that means that it's zero velocity. If you have a linear graph, constant gradient, constant velocity, increasing or decreasing. You can even have negative gradient, which in this case means negative velocity, which means the object is moving backwards. We'll look at this in more detail on the next slide. For now, let's look at another analysis, which is the area under the graph. To calculate the area under the graph, it's x times y, which means time times displacement. So try to recall if there are any quantities that is equivalent to time times displacement. It feels weird, there isn't any, right? Even if you want to check by units, where second times meters, you don't get meters per second, it's times. So you get seconds meters or meters second. There's no quantity that comes to mind about this, right? Yeah, which means in this case, again, there is nothing represented with the area under the graph. So as I mentioned earlier, just because we can calculate it doesn't mean it exists. We only want to look at the meaningful calculations. So for displacement time graph, area under the graph is not used as part of the analysis. So now let's take a look at how to analyze the different shapes of the displacement time graph. So remember that for the displacement time graph, any additional analysis can be done with understanding the gradient. We look at the first graph, we have zero gradient because it's a flat line. Displacement is not changing from beginning to end. Therefore, the velocity is zero. So, because the gradient of a displacement time graph is equal to the velocity. For a displacement path with a positive gradient like this, we have constant positive gradient. This tells us that the velocity is also constant with a positive value. Now, then, if we have a graph that gives us a constant gradient but negative, this means it's moving backwards, as evidenced by the shape. You can see it's moving towards zero displacement. So moving backwards, and when you look at the gradient, it's a constant value but negative. So you get a constant negative velocity. Negative means moving backwards. And you can see that, yes, this is proven. So similar to the earlier graphs that we saw, and you have graphs with changing gradients. In this case, the velocities are changing. So an increasing gradient tells us that the velocity is increasing. Whereas a decreasing gradient graph tells us that the velocity is decreasing. So this is an overview of the displacement time graph. Next, let's look at velocity time. So again, as before, always look at what's on the x and y axis. So for velocity time graph, this shows us the velocity of the object at that point in time, the instantaneous velocity. So just like how we analyzed the speed time graph, the only difference here is that velocity has direction. We're looking at how fast the object is moving relative to its original direction. If we have the section of the graph where the velocity is zero, means zero velocity. If the velocity is changing like this, increasing velocity. So it could be a curve, it could be a straight line, it could be decreasing velocity like this. So for this section, you have to understand that it's not moving backwards. It's still moving forwards because the velocity is positive, but it's slowing down with regards to that direction. The velocity is decreasing, but still going in that direction. The object is only moving backwards when the velocity is negative. So even here you could have straight lines or curves or a constant. A common mistake that a lot of students make is that they think that this tells them that the object is moving backwards. It's not. It just tells us that the velocity is decreasing. So here, I'll put it this way, it's still moving forward. It's only the section below the time axis when the velocity is negative that the object is moving backwards. Okay. So here, the object is stationary, then it's increasing velocity, increasing, and it's slowing down. Then only from this point, it starts moving backwards. And it's getting faster in the opposite direction. To make this easier for you, always analyze in terms of the gradient, because as we know by now, we can use a gradient for analysis. So the gradient of a velocity time graph, let's take what's on the y-axis, which is velocity, x-axis, which is time, you get velocity over time. So what quantity is equivalent to velocity divided by time? So this is now where those of us who have learned the vectors know. Yes, this one, acceleration is change in velocity over time. So acceleration is the change in velocity over time, and therefore the gradient of a velocity time graph is equal to the acceleration. Again, anytime you just want to double check that you have got this correct, you can check the units. Velocity is meters per second, same unit as speed. Time is second. Meters per second divided by second gives us meters per second squared, which is the unit for acceleration. So remember that anything the gradient shows us, that's what the acceleration is, whether by value or whether it's constant, increasing, decreasing, positive or negative. We're going to, of course, look at this in more detail on the next slide, but just a quick overview. You can see here, zero gradient, so zero acceleration, constant gradient, constant acceleration, and so on and so forth. Constant velocity, zero acceleration. Negative velocity means it's slowing down. That's why you get negative acceleration. Now, before we move on, let's just do a quick check with the area under the graph. So for area under the graph, it's the product of x and y. X is time, y is velocity. So which quantity do you know of that is equivalent to the product of time and velocity? That's right, displacement. For those of you who can't see that relationship, remember velocity is displacement over time. So if you bring time up, you would get displacement equals to time times velocity. And you can see, yes, they're pretty much the same thing. So area under the graph is equal to displacement. Whoops, I've written on my cute avatar over there. And to prove this, you can also check the units again just to be on the safe side. So we know time is seconds, velocity is meters per second. Second times meters per second, cut the seconds, you get meters, which is the unit for displacement. So yes, area under the graph is equal to displacement. Let's take a quick look at the different shapes of the graphs. So for the first graph, we have constant velocity or zero gradient. So zero gradient, therefore acceleration is zero. A zero acceleration here means constant velocity. Move my face out of the way so that we can see this more clearly. For the second graph, we have a constant gradient that has a positive value. So constant positive gradient means constant positive acceleration, which should make sense because if an object is accelerating, it means its velocity is increasing. Whereas if you have a graph like the third one where the velocity is decreasing, this gives us a constant negative gradient because the graph is moving down. So if it's moving down means the acceleration in this case is negative. So it's a constant negative acceleration, which could mean deceleration in this case. So is it decelerating? Yes, because the velocity is decreasing. And as always, with the last two, you have a changing gradient. Changing gradient means changing acceleration. So an increasing gradient means increasing acceleration. Please don't mind my handwriting. It's because I'm writing as quickly as I can so that we can go on to the next section. So decreasing gradient means decreasing acceleration. And regardless of whatever shape the graph is, the area under the graph is equal to the displacement. And as mentioned earlier, you can also see from the shapes. So like in this case, this graph would give us a rectangle shape. So the area is a rectangle. The displacement is equivalent to this value. So for these two graphs, you'll have a triangle shape. Whatever value you calculate from this triangle, half base height, that would be the displacement. And if you look at a triangle compared to the triangle is half the value of the rectangle if we measure up to the same velocity. And that should make sense, because if an object is moving with constant velocity compared to an object that is increasing velocity or decreasing velocity, obviously an object that's moving with constant velocity would cover a greater displacement compared to a changing velocity. So when you look at area, that is also shown very clearly. Greater area, therefore greater displacement. Let's go on to acceleration time graph. Now the acceleration time graph is quite rare. We normally don't study motion by using an acceleration time graph because the acceleration doesn't really show us the object's motion. Why? Because if you can recall, zero acceleration could mean two things. It could either mean the object is not moving, or the object could be moving, but at constant velocity. So seeing this graph does not tell us whether the object is moving or not. That's why we generally don't favor acceleration time graphs. Having said that, we still need to learn how to analyze it. So I'm just going to make this graph a bit more complete. You can have, of course, an increasing acceleration with curves, or you could have decreasing acceleration or even negative value accelerations. That's possible. Let's look at the analysis in more detail. So we're going to learn about the gradient and area under the graph and how we could use those to analyze the acceleration time graph. Starting off with gradient. So gradient is y over x. From this acceleration time graph, acceleration is on the y-axis, while time is on the x-axis. So this gives us acceleration over time. Now, try to recall if there are any quantities that is equal to acceleration over time. Can't think of any, right? That's because there are no quantities equal to acceleration over time, which means that the gradients of an acceleration time graph do not have any meaning for us. As I had mentioned earlier, just because we can calculate it doesn't mean that we need to use it. So we can calculate the gradient of an acceleration time graph. We can, zero gradient, constant gradient, changing gradient, negative gradient, we can. But it doesn't mean anything, so we don't have to use that value. Just to further prove that it bears no meaning, we can check it with the units. So acceleration is meters per second squared, time is second, meters per second squared divided by seconds gives us meters per second cubed. So there's no quantity you've learned with this unit, so no need to use. Let's look at the other method of analysis, which is the area under the graph. So for area, we know that area is x times y. That would be, in this case, time times acceleration. So try to recall what quantity is equivalent to time times acceleration. That's right, velocity. So for those of you who like, hey, where did that come from? Remember that acceleration is the change of velocity over time. So it's going to write velocity here. So when you bring this up, you would get velocity equals to time times acceleration. So from here, you should be able to see the relationship where area under the graph is equal to velocity. And to just double check, again, we can use the units. Time is seconds, acceleration is meters per second squared. So seconds times meters per second squared, you cut one of the seconds off, you get meters per second, which is velocity. So the area under the graph for an acceleration time graph gives us the velocity. So although I've mentioned that acceleration time graph is not very popular, just to make this feel a little bit more complete, we're going to look at the similar shapes of the graphs as earlier, but for the acceleration time graph in this case. So for these graphs, remember that the gradient doesn't represent anything. The area, on the other hand, would represent the velocity. So I'm going to write that down. Area under the graph represents the velocity. So if you wanted to get the velocity from an acceleration time graph, you would calculate the area. For example, the rectangle, the triangle, or if you could differentiate the curve graphs, that would be the area, that would be the velocity of that particular motion. Because there's no gradient to speak of, any analysis you need to do, you can do a general description in this case. So for example, for the first graph, this would be a constant acceleration, which means increasing velocity. This is an increasing acceleration, decreasing acceleration. Both of these are at a linear rate. This is increasing acceleration at an increasing rate. Let me write here for the others. This is constant rate at constant rate. And the last one is increasing acceleration, but at a decreasing rate. Okay, I apologize for my writing. We're almost at the end of this video, so I'd just like to move on so that we can call it a day. Remember that the same shape is not the same motion. So for example, for the displacement time graph, this shows us a constant displacement or zero velocity. For velocity time graph, this shows us constant velocity at zero acceleration. So remember, same shape doesn't mean same motion. This shows us constant acceleration. For the graphs with linear lines like this, we have constant gradient. So this is constant velocity. For the velocity time graph, this is constant acceleration. And this is just increasing acceleration. For the graphs with negative gradients, for the displacement time graph, this shows us a constant negative velocity. I'm just going to write negative in front, constant negative velocity, constant negative velocity. For the velocity time graph, this is showing us constant deceleration. And this acceleration time graph shows us decreasing acceleration. This is increasing velocity. For this is increasing acceleration. This is also increasing acceleration, but not the same rate as for velocity time graph. I'm just going to write here increasing acceleration. Then for those with decreasing gradients, for the displacement time graph, this is decreasing velocity, this is decreasing acceleration. So by the way, decreasing acceleration does not mean the same thing as deceleration. Deceleration means negative acceleration. The velocity is decreasing. Here, the velocity is increasing, but the rate at which it is changing is decreasing. So this could be, for example, be seen in vehicles that are moving fast, and as it approaches terminal velocity or the highest velocity it can reach, it will no longer accelerate, but it is still moving at a high velocity. I just want to point it out because that's a common mistake a lot of students make. And for the final one, this is increasing acceleration, but at a decreasing rate. So as mentioned in an earlier slide, the same shape is not the same motion, but you can have different graphs with different shapes showing the same motion. Where can you see that? For example, over here, we have constant velocity at zero acceleration, and here we have constant velocity. So this means that these two graphs could be potentially showing us the same motion, because this shows us constant velocity, and so does this. Similarly, this graph is showing us constant acceleration. This graph is also showing us constant acceleration. So these two graphs are showing us similar motions. And you can see here you've got increasing acceleration for this graph. You also have increasing acceleration for this graph. These two graphs could be showing us the same kind of motion. While decreasing acceleration, you have this graph as well as this graph. So these two graphs could be showing us the same motion. Now, I highly recommend that you don't memorize which graph shapes show us the same motion, because this is not something that's commonly tested in your exams. Rather, if you can understand how to analyze these graphs in terms of the shapes, the gradients, as well as the area under the graph, you should be able to figure out what the shape should be for that particular graph, whether it's displacement, velocity, or acceleration, and from there you should be able to compare and find whether they're the same motion or not. And now we've come close to the end of this video. So just as a summary, let's go through the relationship between displacement, velocity, and acceleration of these motion graphs. So remember that it starts from displacement, moving forward to velocity, and then acceleration. So if you have a displacement time graph and you would like to get the velocity, you would calculate the gradient. So calculating the gradient of a displacement time graph will give you the value of the velocity. If you are given the velocity time graph and you would like to calculate the acceleration, you would also calculate the gradient. So the gradient of a velocity time graph will give you its acceleration. Then if you want to calculate displacement from the velocity time graph, you would calculate the area under the graph. And if you're given an acceleration time graph, to calculate the velocity, you would calculate the area under the graph. So if you need to remember this, what you can do is just write displacement, velocity, acceleration. Moving forward, you would calculate the gradient. Moving backwards, you would calculate the area under the graph. And that is it for this lesson. So I hope you found this video to be educational and helpful. Please help me keep making free educational video lessons and lab practicals. Donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. Of course, if you just like to have free lessons instead, that's fine. Just subscribe to my YouTube channel where I'll be happy to share a lot of free physics lessons. And if you'd like notes, quizzes, and syllabus updates, you can find more information at my website at physicsrocks.com. Happy studying!